So good morning, everyone. Welcome back for calculus. Today we're going to focus in on the next section. So we're going to be starting sections 10.6 and 10.7, which I kind of merged into one long packet on the alternating series, the ratio test, and the root test. What we're about to start tends to be somewhat powerful and also a little bit more straightforward, which is a nice combination. We like things that are powerful and straightforward. I think it'll be good. We've got 3 days on this packet. We'll probably get through most of alternating series today, and then we'll have Thursday and Friday to talk about the ratio and the root test, which you've already all played with at least somewhat in Calc 3 already. So that's a good thing. So you already have some sense of what's coming. So good, that's good news. Before we dive into the material, let's just go through our announcements. So when last we saw our intrepid heroes, they were studying about the comparison tests, and we talked about 2 different comparison tests, the direct comparison and then also the limit comparison test. When we were going through those sections, I shared an example 2, where I just was flat out wrong. I was trying to make a valid point, but I used the wrong example for that. And so as I posted on Slack, I adjusted the question to make the point that I wanted, posted the video clarifying what should have happened on that particular example, and then also incorporated the new version into the online class video. So if you didn't get a chance to take a look at that, please do so. I'd appreciate that. I think it'll help you understand what we were trying to do in class yesterday. Should be a little clearer. Today we're going to start by looking at one of the easier tests, namely what's called the alternating series or alternating series test. So let me share my screen. Again, this is the beginning of section 10.6, and we've kind of are blurring it sort of directly into 10.7. So beginning of sections 10.6 and 10.7. All right, so we are going to be talking about alternating series. So the convergence tests that we have looked at so far apply only to series with positive terms. In this section and the next, we learn how to deal with series whose terms are not necessarily positive. Of particular importance are alternating series whose terms alternate in sign. And so I have a couple of examples right here at the outset. So notice that this top example goes plus, minus, et cetera, et cetera, et cetera. And the lower example goes minus, plus, et cetera, et cetera, et cetera. So both of these would be alternating series where the terms are alternating between positive and negative. One thing to note is that in the top sequence, when we collapse things together, we have a -1 to the n minus 1, and the lower series we have -1 to the n. It's this expression here that makes things alternating. So if you see a -1 to the power, that tells you it's going to be alternating. If you want to create an alternating series, then you would put a -1 to the n power. The n and the n minus 1 are there to help determine whether you want to start with a positive term or start with a negative term. And my pro tip is that rather than memorizing some formula, I would encourage you to just try one of them. Most likely, if I was trying something, I would probably start by trying a -1 to the n power, and then write down the first few terms, beginning wherever your index starts, and see whether it has the pattern you want. So if it lines up, then you keep it. If it has the opposite signs, then just change it from an n to an n plus 1 or an n minus 1. Are there any questions about that? Very good. So in this next little bit, I want to draw a distinction, or I want to separate some things out. So what we want to do is we want to say that our terms A, that these terms here are alternating in sign. So they're going some version of plus minus, like that. But I want to separate out the alternating bit from the non-alternating bit. And so I'm going to create this BN term, and the BNs are always going to be positive. Or maybe I should say non-negative. And so the BNs are always going to be non-negative, and then I can multiply them by the -1 to whatever the power is to make them alternating. And this is going to give us a little bit of a vocabulary later on that will help us to distinguish between the alternating part and the non-alternating part. Questions about the difference between the A's and the B's? Very good. So the next example I'd like to look at is what's called the alternating harmonic series. Let's switch over to our other camera. So do you remember the the harmonic series? The harmonic series was the sum from n equals 1 to infinity of what?
1/2 quarter.
Yeah, so it's just 1 over n. So this would be 1 plus 1/2 plus 1/3 plus 1/4, et cetera, et cetera, et cetera. So this is the harmonic series. So the alternating harmonic series is going to go 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus et cetera, et cetera, et cetera. So it's the same terms as above, but now they're alternating plus minus, plus minus, plus minus, et cetera, et cetera. Let's see if we can write down the formula for that. So this would be the sum from n equals 1 to infinity. And what I want to do is I want to distinguish between the signs and the magnitudes. So our magnitudes are still a 1 over n. So that 1 over n will, this part here is enough to handle the 1, the 1/2, the 1/3, et cetera, et cetera. But then we need a second term that can handle the fact that we're going plus, minus, et cetera, et cetera. So like we were talking about below or above, we can make this a -1. Maybe let's make it to the nth power and see what happens. My -1's not very clear. -1 to the nth power. Let's see how this works. So if we go -1 to the nth power, so when n equals 1, this would be -1. When n equals 2, this would be -1 squared or +1. When n equals 3, this would be -1 again. Is this the signs that I want?
Nope.
Not so much. So what we can do is we can either add 1 or subtract 1 from this exponent. It won't make a difference. Maybe I'll add 1 to it, and suddenly all those signs are going to change. So now it's -1 to the 2th plus 1, -1 to the 3rd -1, -1 to the 4th plus 1, et cetera, et cetera. So we need to have that -1 to the n plus 1. Golly. Just ran out of a little bit of space there. Questions about where the formula for the alternating harmonic series came from?
Oh, never mind. You answered it.
Very good. All right. So let's see if we can look at the manipulate to try to understand what happens to these terms. So let me go back to sharing screens. Okay. So let's look at this series that we've got established. So the terms are -1 to the k plus 1. We were using n's, here it's k's, same thing. So -1 to the k plus 1 over k. So this right here is the alternating harmonic series. Is it weird if we call it the harm? We could call it the harms. That sounds kind of dire, doesn't it? The alt harm s. Okay, I like it.
It sounds like a disease.
Yeah, it's a disease. But we'll leave it that way, at least for today, because it's kind of entertaining. It won't hurt you. Actually, it might help you quite a bit, but it looks bad. It could harms you. Yeah, be careful here. So this is it looks like the alternating harmonic series with one slight distinction. Notice that we have an n in as our upper value in our summation. So that tells us that this whole expression represents what? It represents there's a term for it. This is Sn, which is what?
Partial sum.
Exactly. Thank you. So as we let n go to infinity, this will approach the full alternating harmonic series. But what we have here is actually just a partial sum of that alternating harmonic series. So let's see what happens as we allow, as we look at those sums. So this first dot would represent S1. So that would just be the very first term. Like this is the same as just A1. So then we put in the second dot. This would represent A1 plus A2, which in our case would be 1 minus a half. And then our third dot, so this is A1 plus A2 plus A3, or you're going to get the 1 minus a half plus a third. Right? I think the pattern is starting to show up. It should be somewhat clear that the terms are bouncing around. Why is it that they have kind of this zigzaggy pattern? Like first it goes down, and then it goes up, and then it goes down. Like why is that happening?
Because it's going from positive to negative.
Yeah, because you're always going back and forth between adding something and subtracting something. Notice that even though we're going back and forth between adding something and subtracting something, the values all seem to be approaching whatever this limit is, right? So why is it that they seem to be getting closer and closer to something if we're always adding and subtracting? There's something special about the numbers that we're adding and subtracting.
They keep getting smaller.
Exactly. Thanks, Damon. So we're adding or subtracting smaller and smaller fractions. And so we're always getting closer and closer to the dashed limit line. That makes sense to folks intuitively? So if you use some techniques that you learned about in Calc 3 around power series, you can actually show that we know this value. This number right here is the ln of 2. That's what these values are approaching. And I haven't worked through it recently, but I would be happy to work through it with anyone if, sorry, that's not a negative. It's just like that's where the value is. But I would be happy to work through it with anyone after class if anybody's like, hey, I don't believe that this is ln of 2. Like, how can we work through that and see that for ourselves and get a feel for it? But this number is approaching the ln of 2, which is kind of cool. Like, why is it that the alternating harmonic series is approaching the ln of 2? Or more generally, what can you tell me about the sum of the 1 over n's? This is which series?
Harmonic.
This is the harmonic series, and the harmonic series does what?
Converge.
Converge.
Wait, what did you say it does?
It converges.
It's the other converge.
Diverges.
Exactly. Good call. It diverges. Like, this is one of our famous, this is one of the entries on the list, right? So this one diverges, but the alternating harmonic series, oh my gosh. That's okay. What does this one do?
Converge.
Converges. If you can remember these two examples, that the harmonic series diverges, the alternating harmonic series converges, oftentimes these two examples can save you a world of grief in your intuition. It's sort of like we get turned around and confused when we're dealing with rational expressions, things where you have x's in the denominator. But as soon as we turn it into numbers and you see that as halves and thirds, you're like, oh my gosh, I know how to work with, fractions with numbers in them. And those fractions with numbers in them can help you to make better algebra decisions. Same thing. Understanding these couple basic examples that are on the list will help you to have a good intuition or a good understanding on more complicated things. Questions? Very good. All right. All right, so we've made it through our alternating harmonic series. Again, let's look at the list. I think my notes are, I think your notes are a little bit different than these, but in mine, remember our list now includes the geometric series, the harmonic series, telescoping series, integral test, test for divergence, p-series, the comparison test, which is kind of weak-ish. Yesterday we learned about the limit comparison test, which is stronger. And now we have that the alternating harmonic series converges. We haven't proved it, but we got a pretty strong hunch at this point that that's what's going to happen. I think I have a second drawing on the handouts for those of you that have the handouts. So let me see if I can go there. Maybe not. Oh, no, it's coming later. Sorry, got ahead of myself. Pardon me. Okay, let's keep going. So while we have only an intuitive sense that the alternating harmonic series converges, we're beginning to see the pattern. And so we see this idea that your first term, your first partial sum in an alternating series will be high, and then we're going to subtract, which is going to take us down low. But then we're going to add something, but the amount we're going to add is going to be less than the amount we took away. And then we're going to subtract, but the amount we subtract is going to be less than the amount we just added. And so we're always kind of coming in and approaching a narrower and narrower band, approaching some sort of a limit L. Let's look at a manipulate for this. So again, here's S1, which is A1. S2 would be S1 minus A2. And so we get up here, and then we're going to subtract out a term. And then here was our S2. We're going to add something to S2 to get to S3. And then we can subtract something to get to S4. Add something to get to S5. And so you can see that the sequence here of S1, then S2, then S3, like all these odd terms, is non-increasing, which is code for going down or staying flat. And it's also bounded below. What do we mean by bounded below? Like, what's this bounded below by?
The limit.
Yeah, sure. It's bounded below by the limit, but maybe even, could you give me a number that's on the graph that it's bounded below by? Like, because we don't know that the limit exists quite yet. So all of these are all the positive terms, and so they are all bigger than what that we can see right on the picture.
It's not bigger than 0, is it?
They are definitely all bigger than 0, true. I might even look at it and say, hey, they're all bigger than S2. Does that make sense? So all these terms are bigger than or equal to S2. Like, why not? On the other hand, the S2, then S4, and then S6 are all increasing terms. So these are all increasing right here. We say non-decreasing because we want to allow for them to be flat. And then we say they're bounded above by what?
Is it S1?
Sure. By S1. If you'd said, well, Dusty, I don't want S1. I want to use S3. That's fine. We could use any of these numbers. They would be bounded above by any of these numbers. But specifically, we know, let's just not overthink and just choose the first one. So it's bounded above by S1, which is equal to A1. Remember that S2 is equal to, in this case, it'd be A1 minus A2 with the way it's set up. And so what we're saying is that the sequence of the S1, S2, S3, all these odd terms is non-increasing and bounded below. Therefore, by the monotonic sequence theorem, it's going to converge. Similarly, the even terms, S2, S4, S8, et cetera, are non-decreasing and they're bounded above. By the monotonic sequence theorem, those are going to converge as well. And so by setting it up this way, we can prove or we can show that the theorems must converge. It's not a full proof, but it's a relatively foolproof method for showing why this is true. Questions?
So what were we trying to prove basically by doing this?
We are trying to, I'm so glad you asked. We are trying to prove the following theorem. Leaving the screen share. Where did it go? That one. We're trying to prove the following theorem. So this is the alternating series test. So if you have an alternating series, if the terms are decreasing, so these are the terms, are non-increasing, and if the terms themselves go to 0, then the series is convergent. So it says the terms have to be non-increasing, they got to be there. It lets the terms be bounded because they're alternating. The limit going to 0 says that the things are getting closer and closer together. And the combination thereof gives us a way of showing convergence. The picture below kind of gets at the same idea. So if you start at 0 and you think about what the sum does, well, you add in your first term, and that gets you to S1. And then we come through here and we subtract out our second term, and that gets us to S2. And then we add in our third term, and that gets us to S3. And then we subtract our fourth term, and that gets us to S4. And as long as the B1, B2, B3, B4, B5 are getting smaller and smaller and smaller, i.e. their limit is going to 0, and as long as the terms are non-increasing, then somewhere in the middle, you're going to get a limit S for that alternating series. Did that answer your question a bit, Joseph?
Yes, it did.
Very good. Other questions before we move forward?
Yeah, sure. So, like, say for instance, when you're talking about the limit going to 0 over here, so taking for example, like all those points of S are the X coordinate, and then you got the Y coordinate. So, with the Y going to 0, is that the implication that it's the same 0 we're talking about here?
Good question. These guys right here, these are not Y coordinates.
Okay.
What I'm trying to do is I'm trying to be entirely on a number line. So I'm entirely on the X, and I'm trying to say, okay, I want to start here and I want to end there and I want to explain it. So to explain it, think about I'm going to go from here to here, and then I'm going to go from there and I'm going to go back. So it's more about trying to just make something clear in like a bouncy type of way. That's how they're drawing it. Does that make sense?
Yeah, almost.
Almost.
So 0 really isn't a point, right?
0 is a point. It would be the partial sum when you have nothing to add, when you haven't added anything.
Oh, okay.
Good. Yeah. Good question.
Yep.
Other questions? Very good.
Actually, wait, what would be like a real world application for this?
Of an alternating harmonic series? Or
Yeah.
Well, and a real world example, good question. So a real world example of this particular series would be, and I'm not saying you're going to end up in this scenario, but if you happen to find yourself on on a desert island, right? And you find yourself in need of knowing the ln of 2. You're like, well, I need to know the ln of 2, and I can't remember what it is, but I just happen to remember how to work with infinite series and power series, which granted seems a little bit unlikely. This would allow you to approximate the ln of 2 to as many decimal places as you want. And since you're on a desert island, you'd actually have a lot of time to do those calculations. So I don't know if that quite counts as a real world example, but I think that the bigger thing that's going on is that the alternating harmonic series itself isn't super powerful. It's just a very, very specific example, but it gives us a nice tool through which to understand alternating series themselves. And you played with alternating harmonic series when you were in Calc 3 and you were working with power series. And I actually am not 100% sure what or how you did it, but when you work with power series, you have to find the radius of convergence and the interval of convergence. Does that ring a bell to people?
Yeah.
Okay. And so when you're finding the radius of convergence and specifically the interval of convergence, you are often having to check endpoints, or you'd always have to check endpoints. And oftentimes the endpoint that you were working with turned out to be one of these alternating harmonic series. Does that help at least a little bit?
Yeah. Let's see.
Yeah. Titus shared another practical example of perhaps rippling waves on water. I'd have to think, I think that would definitely give the idea of the up-downness and the idea of it going to 0. I'd have to think about what the series component, like the adding up component of that would represent. But I think that at least that would be a nice picture of what would happen. Like if you took a rock and you threw it into a smooth pond, something like that. Other questions before we go on? Very good. All right, so let's look back at the list. We are now, believe it or not, up to 10 items on the list. Some of these things are tests. I think I can, here's oh no, not that one. Some of these things are tests. So there's a test, there's a test, there's a test, there's a test. Others are more of like specific examples. So we've got some specific examples like the alternating harmonic series and the harmonic series. We have one formula. We have our nice geometric series formula. We like that one. And then we also just sort of have one last example that's just like an approach or a concept, and that would be working with telescoping series. But these ones are like to be avoided. Like only take this approach if you have to. Okay. So we introduced this idea of the alternating series or the alternating series test. It's pretty easy to work with, and we're going to do some examples in a moment. But before we get there, I want to introduce a concept called absolute convergence. And so absolute convergence says, does the series converge if you take the absolute value of the individual terms, if there's no plus minusness about everything? Okay. And so if something is absolute, if something converges with the absolute value, then we call it an absolutely convergent series. So if the terms in a series are all positive, then absolute convergence is the same as convergence in that case. So really, this idea of absolute convergence is only relevant when you have an alternating series. So it's only relevant when an alternating series. Questions? Very good. All right, so let's look at a couple of examples. So here we are in example 2a, and I have the sum from n equals 0 to infinity of -1 to the n, 1 over 2 to the n. And so we want to know, is this series convergent or divergent? And if it's convergent, is it absolutely convergent? And so what we can do is we can start by asking, is it convergent or divergent? Which kind of series is this?
Geometric? Yes.
Alternating harmonic.
Like, I think I think alternating would be correct. I think geometric is actually correct, but in this case, what I was after was, I was after you looking and recognizing that there's this -1 to the n. And as soon as you have that -1 to the n, you should think, let's try the alternating series test. Like, it's just sort of like a go-to, easy to recognize characteristic of a series that should be an immediate tip-off to at least consider the alternating series test. Although you were also correct, Damon. So if I wanted to do the alternating series test, I have to look at two conditions. I have to say, are the terms decreasing? And what I mean by that is, I mean the terms 1 over 2, 1 over 4, 1 over 8. I guess I also have 1. So if I'm putting in n equals 0, n equals 1, n equals 2, n equals 3, et cetera, are these terms decreasing? Yeah, happy yes. And then how about the limit? What's the limit here?
0.
Happy 0. Okay, so it's happy 0. And so since the terms are decreasing, since the terms themselves go toward 0, what can we conclude?
Is
Converges. And how do we know? Converges by which test?
alternative tests.
Yeah, by the alternating series test. Sweet. So at this stage, we're feeling pretty good about ourselves. And then we go back to the directions, and the directions say, is the series convergent or divergent? If it's convergent, is it absolutely convergent? And we think to ourselves, drat, we just showed that it converges. Now we have to ask ourselves, is it absolutely convergent? So to do that, we're going to go back up to the top and ask, is this absolutely convergent. Okay. And so we got to look at the series from n equals 0 to infinity of absolute value -1 to the n, 1 over 2 to the n, which simplifies to, when you take that absolute value is going to undo the -1 to the n part. So we're just going to have a 1 over 2 to the n. And as Damon recognized earlier, what kind of series is 1 over 2 to the n?
Geometric.
Geometric.
It's geometric. And is it convergent or divergent?
Convergent.
Okay. So it's a convergent geoseries with r equals 1/2. In case you're wondering, yes, you could have come back up here at the start and written this as -1/2 quantity to the n, which would be a convergent geometric series with r equals -1/2. So you could have done this all in one shot if you were so inclined. So it's a convergent geometric series with r equals 1. So what does this tell us? Therefore, the series -1 to the n, 1 over 2 to the n is what?
Absolutely convergent.
Absolutely. This is absolutely convergent. Something like that. Questions about the two parts of the question of the example? Sorry, it's a little bit long. Very good. So let's look at another example. So in example 2b, we've gotten smart, right? And we realized, hey, maybe let's just try for absolute convergence and see if that's going to work. And let's just save ourselves a little bit of time. So let's look for absolute convergence. So we consider the sum from n equals 1 to infinity of the absolute value -1 to the n minus 1 is 1 over root n. What are those absolute values going to simplify this to? Just the sum from n equals 1 to infinity of what?
One over square root n.
What kind of series is that?
It's a power. It's a P series.
P series.
Good. And does it converge or diverge?
Diverge.
Diverges. So what does that tell us about the series that we started with?
It does not absolutely.
Nothing.
Yeah, nothing. Well, it's a little bit better than nothing. It tells us that it doesn't absolutely converge, right? That would be like telling if you said, "Hey, Dust, what are you doing today?" And I said, "Well, I've decided to not go to Hawaii." You're like, "You're not going to Hawaii? Well, what are you doing?" Like, there's so many different. You're like, "What? We've ruled one thing out, but there's lots of other options." So it tells us something, but not a lot. It's like saying I'm not going to Hawaii. Although Hawaii does sound kind of nice today. So what do we still need to try to determine? So it does not absolutely converge. We still need to figure out whether the series
Converges or diverges.
Converges or diverges. And so what test are we going to use to determine if this series converges or diverges?
Alternative series test.
Alternating series test. And again, we're focusing in on that -1 to the power, which tells us it alternates. So let's try our alternating series test. Some ragged paper in my pile. So if we tried the alternating series test, we need to know, are the terms decreasing? Decreasing, I want to know if 1 over root n is decreasing. So this would be 1 over 1, 1 over root 2, 1 over root 3, 1 over root 4. Are these guys decreasing?
Yes.
Yep. And so then we got to look at the limit as n goes to infinity of the terms, 1 over root n. What's that limit?
0.
0.
Happy 0. So therefore, the series from n equals 1 to infinity of -1 to the n minus 1 times 1 over root n does what?
Converges.
Converges by which test?
Alternating series test.
Yeah, by the alternating series test. Very good. So when we pull this back together again tomorrow, what we will do is we will look at one other type of convergence, and we'll say that a series could be convergent or divergent. If it's convergent, we'll talk about how it could either be absolutely convergent or conditionally convergent. The first example, 2a, was an example of a series that was absolutely convergent. The example we just did, 2b, is an example of conditional convergence. And we'll talk a little bit more about that tomorrow, yeah, as well as other things. But in the meantime, may you all have a wonderful day. May there be some wonderful harmony where things come together, where the music of the world around you sounds beautiful. And I look forward to seeing all of you tomorrow. Have a wonderful day. If you have any questions, feel free to hang on the line. Take care, everyone.